Hey, polar bears and polar cubs, double replacement. It is one of the coolest kind of reactions. And the reason is it's kind of called the do-si-do. So what happens is you might have two people that are partnered up, and then at a certain point, they switch partners in the dance. Okay. And that is what the double replacement is. For double replacement, traditionally, both of these are aqueous. And the reason I say that is you can't have a double replacement reaction where you have a solid, you pour an aqueous solution on top of it, and things occur. It's far easier for the reaction to occur once they become aqueous. So this is compound number 1. This is compound number 2. And then what happens is they switch partners. A wants to dance with Y, B wants to dance with X, and you get a nice new compound. And we'll call that new compound number 1, and you get a second new compound. And that's what happens in double replacement. But there's a catch. And the catch is with double replacement, you have to have something that drives the reaction to occur. So you have to have something called a driving force. And what this means is that on the product side, you must form something that is either a solid, a liquid in the form of water, or some kind of gas. Now, I'm going to be kind of generous, and the only two gases that you're going to need to remember that could be formed are NH3 and CO2. Well, it's nice of me, but it's also a little bit difficult to remember those two, because these are the two things that if you do the double replacement, these would come out on the product side. However, they never actually form. And I'm going to use H2CO3 as the prime example. H2CO3 is called carbonic acid. You all have seen it in a carbonated beverage like pop. And as soon as you pour your pop, or as soon as you open your pop, the CO2 gas is trying to get away, which then leaves just water behind, which then gives you that taste of a flat pop. It tastes watered down and things like that because it's flat. So these break down as soon as they form, and they will always form the gas and then water. I like to, on this side, write water as H2O, just because it will balance. Because they come from the same formula but get broken up, whatever coefficient you would have put here is what you would then put here in both of them. It makes balancing a little bit easier. I always write this and then balance and break it apart. Okay, if no driving force occurs, we're just going to write no RXN. That's a very common thing that happens. In real life, no reaction happens, so you write no RXN. There's no driving force. So let's look at how do we determine if something is a precipitate. In order to determine a precipitate, we're going to use the solubility rules. These are found on the back of your periodic table, and we're going to read through them together just now. So the solubility rules. Rule number 1 tells you that all compounds containing alkali metal cations and ammonium cations are soluble. Well, these are group 1, so they are 1A. That's those cations. And this is NH4 plus. All of those are soluble. If you see that in one of your products, you automatically know it's soluble. Number 2, it says all compounds containing nitrate, perchlorate, chlorate, and acetate are also soluble. So any cation attached to those anions would then be soluble as well. The word soluble equals aqueous. So then number 3, all chlorides, that's Cl minus, bromides, Br minus, iodides, I minus, are soluble. But if they're in a compound that contains silver, lead 2, or mercury 1, they're not. So when it says except, that would mean that these 3 would be our precipitates. They're solids. Number 4, it says all sulfates are soluble, except, again, these 5 different cations. So these 5 different cations would make a solid attached to a sulfate. Question number 5 on the solubility rule says all hydroxides are insoluble. So they are now insoluble, meaning they're all solids, except for when they are contained with alkali metals, which is, remember, we said that is group 1 on the periodic table. And these 3, calcium, strontium, and barium. Finally, you have number 6 on the solubility rules, and that is all compounds containing phosphate, sulfide, carbonate, and sulfite are insoluble. Remember, that would mean that it is a solid, except for when they contain those 2 cations. Well, those cations, solubility rule number 1 told us they were soluble. How it goes is most important. So it goes from like star to the period. Pretty much most important to least important. So let's go ahead and let's apply these. So we're going to do the first 2 together. Then I'm going to give you guys the opportunity to try 3 through 5 and check them. So first thing that we're going to do is we're going to decide who goes together. So, oops. I underlined the 2 anions. I put a another line on top of the anion or cations. So this anion of Cl will go with this cation, and then this anion will go with this cation. So you're going to get NaCl. Now Na is part of those group 1s. So that's aqueous. So I know that that cannot be our driving force. We need to have a driving force. On the other side, we're going to get calcium carbonate. Now, in order to write these formulas, Na's got a +1 charge. This has a -2 charge, +2, -1. So when I bonded them, I needed to use those charges to get subscripts. Let's look at the solubility rules. And solubility rule number 6 tells us that all compounds containing carbonates are insoluble unless they have those anions. Or cations, my bad. It does not have one of those cations, meaning that this is a solid, and right here is our driving force. Once we've identified the driving force, we would go ahead and we would balance it. I'd see that there's 2 Cl's, 2 Na's, put a 2 there, and we're balanced. We're going to go ahead and try number 2. Number 2, you have ammonium and hydroxide going together, and you have nitrate and sodium. Remember, we always do cation first, so we're going to do sodium and nitrate. I'm going to go ahead and look at the solubility rules. Those solubility rules hit 1 and 2, telling me that it is for sure going to be soluble. And then on the other side, I'm going to get NH4OH. When I look at this, this is also soluble. So it's looking like it's a no reaction. I know for a fact that it is because this cannot form. What it does form is NH3, which is a gas. That's a driving force. plus HOH, which is a liquid, which is also a driving force. This one just happens to be balanced. All right. That is double replacement. You do need to be able to use the solubility rules, get familiar with them, read through them, kind of be able to justify which rule is telling me on which product. I'm going to have you go ahead and try 3, 4, and 5. Go ahead and pause it and then give it your best shot. I'm going to be giving you those answers here just shortly. 5, 4, 3, 2, and 1. On this, you're going to produce sodium chloride. This is aqueous, plus then H2CO3. This is an acid. It's aqueous. However, I know that this reaction occurs because that actually breaks up into water, liquid, plus CO2 gas. How do I balance it? It is balanced. I have 2 H's on the left, 2 H's on the right, 3 O's, 3 O's, 1 C, 1 C, so on and so forth. So on the next one, on question number 4, magnesium has a +2 charge, so it's Mg, NO3, 2. This is aqueous due to solubility rule number 2. NH4 and SO4, so there would be 2 of these. SO4. NH4 automatically makes everything aqueous. If they are both aqueous, it is a no RXN. So if we can't tell something happened, nothing happened. Let's try the last one. Last one, you're going to get AgCl plus CaNO3 in parentheses 2. This is soluble due to rule number 2, being a nitrate. AgCl, well, Cl, that's a chloride right here, number 3. It tells us they're soluble except when containing silver. So therefore, this one has silver attached to it. That makes this a solid, and all we have to do is then balance it. We would put a 2 here and a 2 here, and we're balanced. All right. Go ahead and watch the video on double replacement reactions for the worksheet. Complete that, turn it in, and let me know if you have any questions.